Welcome to This Explainer. Today, we're diving deep into something absolutely crucial, but completely invisible: the nervous system that keeps spacecraft alive. I mean, have you ever actually wondered how we talk to satellites, or how they manage to survive out there in the dark? Well, grab a seat, because today we are going to break the whole thing down.
Right off the bat, let's just think about the sheer, mind-boggling engineering challenge here. We are trying to establish a flawless, incredibly high-stakes communication link with these complex machines that are just floating out in the unforgiving vacuum of space. How do you control a machine moving at thousands of miles per hour, potentially millions of miles away, especially when a single, tiny misunderstood signal could literally mean the sudden end of a billion-dollar mission? It's intense. So let's get into it with Section 1, the spacecraft nervous system.
To really understand this invisible system, we have to look at the digital bridge between our ground stations here on Earth and the cold reality of orbit. Take a look at the telemetry and telecommand block dead center in this architecture. It acts exactly like a central nervous system. It's routing all this critical information to and from the power, thermal, deployment, and payload subsystems. The central hub is constantly receiving commands from the ground, decoding them, and distributing them, while at the exact same time, it's gathering health and status data to shoot back down to us. It is, for sure, the ultimate middleman.
But, the nature of this connection changes drastically depending on where the satellite actually is. For instance, geostationary Earth orbit or geosatellites, they kind of have it easy. They enjoy this relaxed, continuous connection to Earth because they're always visible to their ground station. Low Earth orbit satellites, though, like Envisat, face a totally different reality. They have to survive on high-stakes, rapid-fire data dumps during these incredibly brief windows of visibility as they streak across the sky. Because of this, LEO satellites absolutely need robust onboard data storage and a super rapid transfer link.
Moving right along to Section 2, telemetry, or basically how satellites speak.
Okay, so we've seen the big picture. Now let's explore how these machines actually sense their environment. The first category of data a satellite sends down is known as housekeeping data. Basically, satellites are constantly checking their own pulse. They use specialized sensors, like thermistors, to monitor the temperatures of equipment boxes and solar arrays. They've got transducers for checking the pressure in their fuel tanks, and sensors checking power supply voltages. They'll even send down individual digital bits just to say, hey, yes, this specific mechanism successfully deployed after launch. A modern communication satellite might monitor up to 1,000 of these engineering parameters, usually sampling them every 30 seconds or so. Next up, we have attitude data. This is information pulled from sun, earth, and star sensors, along with gyroscopes and accelerometers. You can think of attitude data as the spacecraft's sense of balance. During really turbulent phases, like the launch and transfer orbits, the spacecraft's velocity and position are changing incredibly fast, so this requires super rapid sampling. We're talking up to 4 times per second, just to make sure the satellite is actually pointing in the right direction. And finally, there's the main event: payload data. This is the actual science, imagery, or communications data the mission was built for in the first place. And the volume here can be absolutely staggering. While housekeeping takes just a few hundred bits per second, payload data, like those massive deep space images we all love, can require gigabits of bandwidth. It's kind of like trying to stream a 4K movie from millions of miles away over a super delicate connection. In fact, if the data rate gets too large, engineers literally have to build an entirely separate high-rate transmission system just to pipe it all down to Earth.
All right, let's jump to Section 3, formatting and fixing data.
So, what does this all mean? How do we package all these completely different senses, the temperatures, the star tracking, the massive images, into one reliable signal that can survive the long journey home? Well, historically, spacecraft used pulse code modulation, or PCM. This is a very rigid time division multiplexing system. Imagine a train where every single seat is assigned to a specific sensor, regardless of whether that sensor actually has any data to send at that moment. Kind of inefficient, right? So engineers revolutionized things by moving to packet telemetry. This is a highly flexible system using variable length packets. Instead of those rigid time slots, data packets are issued asynchronously by any data source at whatever length is needed right then and there. Boom, no wasted bandwidth.
As you can see in a packet telemetry flow, variable length source packets get assigned to what are called virtual channels and are then multiplexed together into transfer frames for transmission. It's remarkably similar to how data flows through the terrestrial internet we use every day. The Consultative Committee for Space Data Systems actually developed these standards, and today, packet telemetry is the dominant technology for missions all over the world. It's exactly what allows interoperability on massive, multi-agency projects like the International Space Station.
But wait, what happens when that radio signal gets super weak? For incredibly distant missions, like when the Huygens probe went out to Saturn's moon Titan, the signal reaching Earth is faint and really prone to corruption. To fix this, without having to ask the probe to resend everything, which would take forever, engineers rely on error control coding. They use a Reed-Solomon block code, which mathematically reconstructs and fixes bursts of errors. Meanwhile, something called convolutional coding gives engineers a 5.1 decibel link margin increase. To put that into perspective, it means they can reliably receive the exact same amount of data using nearly a quarter of the transmitter power. That is a massive game changer.
Okay, let's flip the script. Section 4, Telecommand, giving the orders.
We spent a lot of time listening to the satellite. Now let's explore how we safely talk back and give it instructions. Ground control sends commands in 3 basic flavors. First up, low-level on-off commands. These are just simple logic pulses to flip a digital switch. Second, high-level on-off commands. These pack a bit more electrical punch to physically drive a latching relay or an RF waveguide switch. And third, proportional commands. These are the heavy hitters, complete digital words that can entirely reprogram an onboard computer or set up really complex registers in the attitude control subsystem.
Now, when an order actually arrives on board, it passes through a telecommand decoder, kind of like the ones used by Intelsat. A really critical feature to point out here is the address detector. Every command unit has a unique hardwired address. This guarantees that the message is accepted only if it's meant for that exact specific subsystem. I mean, you definitely don't want to accidentally fire a thruster when you only meant to turn on a heater, right?
And speaking of safety, Intelsat relies on this incredibly rigorous safety loop. Because a single misunderstood bit could literally ruin the entire mission, they use a strict command, verify, execute strategy. Step 1, ground control sends the command and the satellite just holds it in a store. Step 2, the satellite uses its telemetry to echo that exact command back to Earth so we can verify it. Step 3, only after the ground confirms it's the correct command do they send an execute tone. The spacecraft absolutely will not lift a finger until that final confirmation is received. But what if you're a LEO satellite? You might be moving so fast that you don't have time for a slow, polite conversation before you slip out of range. Well, for agencies like ESA and NASA, the checking happens directly inside the decoder itself. They use 2 out of 4 redundant coding and Hamming code check bits. Basically, the spacecraft evaluates the incoming command mathematically right on board. If a single bit gets flipped by a stray cosmic ray on the way up, the satellite instantly detects the error, corrects it itself, and executes the command safely. No Earth confirmation needed.
So let's wrap this all up with a quick look into the future. With spacecraft buses requiring more and more autonomous data processing, correcting their own errors, managing flexible data packets, constantly monitoring thousands of health sensors, it really leaves us with a fascinating question. As spacecraft designs keep evolving toward true autonomous operation, will the satellites of tomorrow even need to wait for our orders at all? Or will this whole spacecraft nervous system eventually evolve into an independent brain? It's pretty incredible to think about. Anyway, thank you so much for joining me on this explainer. I really hope this helped you decode the amazing technology keeping our spacecraft alive out there. Keep learning, and I'll catch you in the next one.